In this video, we're going to take another look at getting information in and out of the CPU. Now you might be asking yourself, why bother? We've already worked out a method of doing this. Well, the method that we worked out is the method that was shown in the original book which this course is based on, and I wanted to put that into the course just for completeness. But there is a simpler way of getting the information in and out of the CPU. As it stands at the moment, we have generated an extra set of commands, that is an extra set of instructions, which are the data in and out, and also the address in and out. Now, we can do it in a simpler manner than that. We can do it by not having any extra instructions. That is, we can use the instruction code that we already have, which in this instance would be the load and store. So we can get data in and out of the CPU using the load and store commands. So if we can do that for the RAM, we can do it for other elements, for example the ROM, and also say input and output devices like a keyboard, mouse and monitors. So this video is going to look at that method, which is much simpler and much neater. And this method is called memory mapped I/O. So let's go ahead and we'll look at that now. So let's talk our way through this diagram here. We can forget about this section here, which is the address decoder and this part of the memory, and also the ROM, the input and the output. All we're interested for the moment is the CPU and the RAM. So we've already seen this before, this little block. We have our CPU, we have our RAM. We want to either write data into this RAM, or we want to read data from the RAM into the CPU. So whenever we write data into the RAM, we're going to have the bus. Now I've just called the bus D, so D for data, and there's going to be an input here. So that's the input of the bus, and that's the output of the bus. Now we know that we've got an input-output here in this instance because Logisim doesn't allow us to have a single pin which we can use for input-output. We have to separate them, so that's why these are separated. So we have our output data, and the data passes into the RAM. Now, in order to decide which address in the RAM, we also have an address bus. So the address bus is just the memory address register, and that's the 8 bits that pass into the RAM to choose which address we're going to either write to or read from. And we also have a control line. Now the control line is nothing other than the two lines, one for set and one for enable, but we just lump them together and we call it a control bus. So in a CPU you're going to have a data bus, an address bus and a control bus, and we've got all three of those items in our little design. Now the control bus will determine whether we're going to write data into the RAM using the set, or whether we're going to read data off of the RAM using the enable. And we've seen that we put this little buffer here, a control buffer, to control the output of data from the device onto the bus. Now equally this little device might as well just be inside the RAM, but we have designed it and we can see it sitting outside the RAM. So I've taken a connection here from the control line just along and round, which controls the data flow out of the RAM onto the bus. So as it stands at the moment, we're going to have data flowing out of the CPU, and then we're going to have the data written into the RAM with the set, and we're going to read data off of the RAM with the enable back along and into the CPU. So we've already seen that, and we know we can do that. We can do that with the data in and out and address in, out. So what we do is we put an address of the device first of all onto the bus so that we know we're pointing to that particular device. And then when we know we're pointing to that particular device, we can then either write to the device using the data out, or we can read from the device using the data in. Now, there's a simpler method for doing that, and that is called memory mapped I/O. So let's say, for instance, that we weren't writing to a RAM, we could be writing to a ROM or some input device or some output device. Then what we could do is we could take our data, our address and our control lines, and we could just simply copy them into the new device. So we've got a new device here with a copy of data, address and control, and the same for this device and the same for this device. And we could also take a copy of the control lines here, which will control whether we're going to write to the device with the set or read from the device with the enable. But then we're still left with this problem that if we were to say, for example, write to the device here, we wouldn't just write to this device, we would also write to this one and this one and this one. Also, if we were to try and read from one of these devices, it would try to read from all four of them. So enable would go high here and here and here and here, and all four of these devices would try to go on to the bus. So there would be an error because we can only enable one device onto the bus at any one time. So we need an extra line which will tell us whether we are going to read or write from either this device or this device or this device or this device. And the question is, where do we get that extra bit of information? Well, we can get that from the address bus. So let's say, for instance, we were to have the address bus which is 8 bits. And let's say we took a copy of, say, the last 3 bits, so the 3 highest bits of that address. We could take those 3 bits and we could put them through a 3x8 decoder. So that is, from the 3 bits we could generate 8 bits. So you've seen the 3x8 decoder before, we've built it and we've used it in various places in the CPU. So we would have 8 control lines here, and we could use these control lines in order to choose which device we're actually going to read or write from. So let's have a look at that and we'll see how that works. Now, I know that we've already built a 16-bit machine, but let's talk through this in terms of an 8-bit machine first. If we were to take the 3 most significant bits over 1 byte into the address decoder, then we would have the 5 least significant bits over byte that would head into the RAM. So we would have an address which would be 5 bits wide. So we could address 2 to the power of 5, which is 32 bytes. So this device here would have 32 bytes that we can address. And the same would for this device here, it would have 32 bytes, and this one and this one. Now, because we've taken the top 3 bits here, then we're going to have the 3x8 decoder, so we're going to have 8 possible outputs here that control which one of these we talk to. So we're going to have the first one which will talk to one of these devices, which would be 32 bits, and then all the way down to the 8th one, which would talk to 32 bits as well. So this would mean the method that we've used here for splitting up the memory is going to split it into equal parcels of 32 bytes. So that's 32 bytes, that's 32 bytes, so's that and so's that, and we've got a potential of another 4 devices here that we can talk to that are going to be 32 bytes addressable. So let's look at an example here of, say, the RAM and the ROM. Let's say, for instance, that the RAM here is going to be controlled by the control line here, but also this first bit of our 3x8 decoder.
So let's say the first bit of our 3x8 decoder comes on whenever the values are 0, 0, 0. So when we get 0, 0, 0 for this 3 bits that come in here, we're going to get this line going high. So this line here is going to come in and it's going to control something inside this RAM here, and it's going to be dedicated to just this block. So it means that at some point here, in effect, the control line is going to get broken. So the control line is getting broken somewhere here. Instead of just having that bus there coming in for the control, we're going to have this bus, and we're also going to have an extra bit of information that comes in. So this extra bit of information is going to tell us that we're dealing with this particular device. And we'll see how we're actually physically going to do that just in a minute. So it would mean that the RAM here is addressable from, well, we're going to have the 5 least significant bits. So it's going to go from 1, 2, 3, 4, 5. And it's going to get the 3 most significant bits from here. Going to be 0, 0, 0. So it's going to be addressable from the bottom of our 256 bytes of addressable space all the way up till, well, it's still going to be 0, 0, 0, all the way up to the value of 1, 1, 1, 1, 1. So that's our 32 bits, 32 bytes, sorry. So that's our 32 bytes, and that's going to be the RAM. So if we put an address onto this bus that's anywhere between these two values, it will always talk to just this device. Because this control line here ensures that it only talks to just this device. We dedicate this line to this device and it tells it that's the device you talk to between these two sets of addresses. And you can see it just forces it to do that because this goes high whenever these 3 bits here are 0, 0, 0. Now, if we were wanting to then look at the ROM would be the next address up. So instead of going from 0, 0, 0, it's going to go from 0, 0, 1 would be this value here. So we'd have this line here, which comes on whenever it goes to 0, 0, 1. And this line here would then get into this device here. And of course, the control line is broken in some way. And this line here, along with the control line, would tell it that we're actually going to talk to this device. And we talk to this device between 0, 0, 1 and all zeros, 1, 2, 3, 4, 5, and also 0, 0, 1 and then all ones, 1, 2, 3, 4, 5. So if we're in between these two memory spaces, then we're talking to the ROM. And we can do that continually for each of the 8 devices. So that's how our memory mapped I/O works. Now, the drawback with what we see here is that we're going to split this in the memory into equal segments. So even if we'd taken, say, just 2 lines out here, then we would have 4 control lines here. And if we had 4 control lines, we would split the 256 bytes into 4 equal blocks. But that might not be what we want to do. And in fact, that isn't what we want to do, because we are going to split most of the memory, which in our 16-bit machine, we're going to split most of the memory into ROM and RAM, and then our input-output. Our input-output is only going to take up a small portion of that. So we don't want to split the device into 2 or 4 or 8 or 16 equal blocks. We want a method of splitting the device into different blocks, say in our instance 3 blocks, a RAM block, a ROM block, and also an input-output block. But the input-output block is only be small compared to the RAM and the ROM block. So we need a method of doing that. And there is a very neat and simple method, but obviously it's still a a memory mapped I/O, we still use the same process here, but instead of taking the top 3 bits out of this here, we've got an option of taking any particular set of bits out and then running those particular sets of bits out. Instead of running through a simple decoder, we're going to run it through some bit of combinational logic, and that combinational logic will then feed back in here, just the same way we have here with our memory mapped I/O, and it will choose the device that we want to talk to, but it will choose it in such a manner that we can break the memory into block sizes which we want to use. So lots of words involved there. Let's just go and we'll build it and we'll see it working, and then it'll be obvious. This is the address decoder for an 8-bit machine. Now we're going to show the 16-bit machine in a minute, but it's much easier to talk through the 8-bit first. Now before I go any further, I have to say that this isn't my design. This was designed by one of the students from the first course called Timothy Morgan, and he has kindly allowed us to use it. And it's really simple and it's really elegant. It's just a lovely little bit of circuit design. So we want to split the 256 bytes for an 8-bit machine into 3 different blocks. One of the blocks will be a ROM. The next block will be a RAM. And then we want a block for input-output devices. We want the ROM and the RAM to take up approximately half of it. And we want the input-output devices just to take up maybe about 16 bytes. And this little circuit ensures that that is the case. So let's talk our way through it. This address decoder is going to take the 256 bytes of our 8-bit machine, and it's going to split it up into 3 groupings. So we're going to have a ROM, a RAM and an input-output. The 256 bytes in hex starts from 00 up to FF. The ROM is going to take up 128 bytes, so it's going to run from 00 to 7F. Now the next location up is a location 80, and from location 80 up to EF we're going to have the RAM, so that's going to be 112 bytes. And the next location up after EF is F0. So F0 to FF will be the input-output, and it's going to take up 16 bytes. So you can see here that the ROM and RAM take up approximately half, and the I/O takes up the smaller chunk of 16 bytes. So let's go ahead and we'll see this simulated. So you can see here with all zeros, we have a 0 in this point here, therefore we have a 1 coming out at the ROM. Now if we were to make the 4 least significant bits high, they're not connected, so there's still no change. And it's not until we got up to this point here. So this point here, we're at the top of the ROM block. And you can see here, if we put this into hexadecimal, we're at 7F. So we run from 00 to 7F in the ROM block. Now the next available location up is 1 and all zeros. And this is us in the RAM. So this is the bottom of the RAM, and you can see if we go to hex, we can see the bottom of the RAM is position 80. And then we can find the top of the RAM if we work our way along here. You can see it changes at that point. If I take the 0 off there, we put 1, 1, 1, 1. So this here is now at the top of the RAM. So if I go into hexadecimal, you can see that's at position EF. And the next location up is going to be the 1 here with all of the zeros. And again, that location is going to be the F0. And we run from the F0 all the way up to the value of FF, which is the top of the
I/O block. So beautiful, simple, elegant, neat little circuit that splits the memory into 3 blocks that we require. So thanks very much for that, Timothy Morgan. That's a fantastic little simple circuit. Now this video has been going on longer than I first anticipated. So let's finish it here, and in the next video we will build up the rest of the memory mapped I/O, and when we're finished on that we can move on to the control section, and that's the really interesting section. So thank you for listening. I'll get you on the next video. Goodbye.